Every time you book a flight or transfer some money or just buy something online, you're placing your trust in this invisible set of guarantees. Today, we're going to pull back that curtain and look at the four letters that make it all possible. ACID. This is the secret sauce, the magic that makes all of our modern software actually reliable. Oh, we've all been there, right? You click pay, you get some weird error message, and your heart just sinks. You rush to check your bank account, and yep, the money is gone. But there's no order confirmation. It is so frustrating, and it just feels completely broken. Well, that exact nightmare scenario is what we're talking about today. That whole mess, that chaotic situation, is precisely what databases are engineered to prevent. And they do it by treating a whole series of actions, like that online purchase, as a single, indivisible unit of work. And that unit is called a transaction. So it feels like just one click to you is actually, behind the scenes, a whole chain of events. The system has to check if the product's in stock, then it has to take your money, then it has to update the inventory count, and then create your order. But what if any one of those steps fails? Imagine the server crashes right after taking your money in step 2. You're just left hanging. Your money's gone, but the order was never placed. I mean, that's the kind of digital chaos that completely destroys trust. So the solution is to bundle all of those steps together into what we call a transaction. And it's a simple idea, but it is so powerful. It means the database treats all 4 of those steps as one single operation. Either they all succeed together, or if just one little part fails, they all fail together and the system just goes back to how it was before you even clicked. And to make this whole all-or-nothing idea really work, databases follow a super strict set of 4 rules. These guarantees are known by the acronym ACID. That stands for Atomicity, Consistency, Isolation, and Durability. So let's break down what each one of these actually does. All right, first up is A for Atomicity. Now, this is the big one, the foundational principle that directly solves our disappearing money problem. Atomicity is the all-or-nothing guarantee. I mean, it's right there in the name. A transaction is treated like an indivisible atom. You can't just have half of it succeed. If any single part of that chain fails, the database automatically rolls back the entire operation, leaving everything exactly as it was before the transaction even began. Okay, check this out. This terminal view shows Atomicity in action. See here? A transaction starts and it tries to update an account balance, but then this line right here forces an error on purpose. Now, because of Atomicity, the database doesn't just freeze. It actively aborts the whole thing, and the proof is in that final check. The balance is unchanged. The attempted update, it's just gone, as if it never even happened. That's a rollback, and it's the safety net that protects your data. Okay, let's move on to I for isolation. So Atomicity protects a single transaction from itself, but isolation protects multiple transactions from tripping over each other. Just think about a really busy website, like for concert tickets or something. You could have thousands of people all trying to buy the very last ticket at the exact same millisecond. If all their transactions aren't properly isolated from each other, the system could get incredibly confused, and that leads to all sorts of weird and just plain wrong results. This diagram shows one of the first major risks. It's called a dirty read. Let's walk through it. Over on the right, transaction 2 starts to make a change, but it hasn't finished yet. It hasn't committed. In the meantime, transaction 1 on the left reads that temporary data. But then, look what happens. Transaction 2 fails and rolls back its change. Well, it's too late. Transaction 1 is now running around with faulty data, a value that never officially existed in the first place. And here's another weird concurrency problem. In transaction 1, we read a value, let's say a balance. Then, a completely separate transaction, T2, comes along and successfully updates that same balance. So when T1 goes to read the balance a second time, the value has magically changed out from under it. This is called a non-repeatable read, and it makes the data feel totally unstable and unreliable. So the solution to all this chaos is something called isolation levels. You can think of them as different rulebooks for how transactions are allowed to interact with each other. A lower, more relaxed level like Read Committed is faster, but it only prevents some of these problems. To get more protection, you have to move to stricter levels like repeatable read. And this is a classic trade-off in engineering. You get way more data safety, but it can come at the cost of some performance. All right, let's bring it home with our final 2 pillars, C and D. These are the ultimate promises that our data will not only always be valid, but that it will never, ever be lost. Consistency is the rule keeper. It guarantees that any transaction that successfully finishes will only ever leave the database in a valid state, a state that follows all of the rules you've defined. It's kind of like a bouncer for your data. And these rules, or constraints, are set up by the developers. They can be simple, like saying no two users can have the same ID. Or they can be absolutely critical, like a rule that a bank account balance can never go below 0. If any transaction tries to break one of these rules, the database itself will just reject it flat out, guaranteeing the data always stays logical and valid. And finally, D for durability. And honestly, this is the ultimate promise. It means that once a transaction has been successfully committed, those changes are permanent. They will survive a power outage, a server crash, pretty much anything. The data is safe, period. So how does it do that? Well, it's through a really clever process called a write-ahead log. Before the database actually changes the data, it first writes down what it intends to do in a special log file. That log gets saved to permanent storage, like a hard drive. So if the power goes out, when the server reboots, it can just read the log and replay any committed changes that hadn't been fully saved, making sure nothing is ever lost. So there you have it. Atomicity, consistency, isolation, and durability. These aren't just some abstract theories for computer scientists. They are the invisible foundation that supports the digital world that we all use every single day. Every single time you use an ATM, buy something online, or book a flight, you are relying on these ACID guarantees. They would ensure your money isn't lost, that your order gets processed correctly, and that your seat on the plane is actually yours. For any system where the accuracy of the data is critical, ACID is absolutely non-negotiable. So I'll just leave you with that final thought. We kind of take for granted that our digital lives are safe and reliable, don't we? But now you know the 4-letter secret that makes it all possible. Without ACID, the trust that our entire digital economy is built on, well, it just couldn't exist.